Welcome back to Stellar Sleep Tales, where we explore the universe one gentle yawn at a time. Tonight, we're easing into a slow, calming journey that touches on one of the biggest questions out there. Where does space actually end? It might sound like a simple or even silly question at first, but the more you think about it, the more it stretches your imagination, just like space itself. As always, I hope this video helps you unwind and drift off peacefully. And if it doesn't put you to sleep, maybe it'll help you zoom out from your daily worries and see things from a few billion light years away. There's a small chance tonight's topic might be a little too interesting and keep you awake, but if that happens, at least you'll walk away with something fascinating to think about. Before we float off into the stars together, I'd really appreciate it if you gave this video a thumbs up. And if you haven't subscribed yet, I'd love it if you joined our sleepy little community. It helps the channel grow and reach more curious minds like yours. Also, I'd love to hear where you're watching from and what time it is for you right now. Are you curled up in bed in Stockholm at 11:30 p.m? Or maybe you're lounging on a couch in Melbourne at 3 in the afternoon, pretending to work while sneaking in a bit of cosmic daydreaming? Drop a comment below. It's always a joy to see our sleepy science family scattered gently across the globe. Now settle in and get cozy. You don't need to remember any of this. No need to take notes or stay alert. Just let the words flow over you like the soft hum of cosmic background radiation. And just a quick reminder, this video is meant for relaxation and education. It's not medical advice or a replacement for professional care. Ready to begin? Let's. Cast, what is space really? That quiet, dark canvas we see when we look up at the night sky. What is it made of? What's actually out there? Most of us think of space as pure emptiness, a giant void. A place where stars shine, planets spin, and somehow socks disappear. But space isn't empty at all. In fact, it's one of the most active, mysterious, and misunderstood parts of the universe. Let's start with the basics. For hundreds of years, people thought of space as just a background, like a stage in a theater. Space was the flat wooden floor, and the planets and stars were the actors moving around on top of it. This idea came from Sir Isaac Newton. He believed space was absolute, a fixed, unchanging arena where everything happened. Time ticked forward at the same rate for everyone, and space was just a three-dimensional grid that held it all together. Then came a man with wild hair and a love for chalkboards, Albert Einstein. He completely changed that picture. Einstein showed us that space isn't just a passive backdrop. It's more like a living, flexible fabric, one that bends, stretches, and warps depending on the mass and energy around it. Space and time aren't separate. They're woven together into a four-dimensional structure called space-time. And this stage doesn't just sit there. It reacts to what's happening on it. To picture this, imagine a trampoline. If you place a bowling ball in the center, the fabric dips and curves around it. That's how space-time behaves when something massive, like a planet or a star, is present. Now imagine rolling a marble across that trampoline. Instead of moving in a straight line, it curves around the dip made by the bowling ball. That's a simple way to picture how gravity works in Einstein's universe. Massive objects like stars, planets, or even Earth bend the space-time around them. And that bending is what we experience as gravity. We don't fall toward Earth because it's pulling us like a magnet. We fall because Earth has curved the space-time around it, and we're gently rolling into that dip. You might be thinking, all right, I get it. Space bends. But what about the parts where there's nothing? The empty stretches between stars and galaxies, aren't those just blank? Not quite. Even in the darkest, loneliest corners of the cosmos, space is still buzzing with activity. Thanks to quantum mechanics, we now know that empty space isn't truly empty at all. At the tiniest scales imaginable, far smaller than atoms, space is alive with what physicists call quantum fields. These fields aren't things floating in space. They are space. Every particle in the universe comes from its own field. Electrons come from the electron field. Photons, which are particles of light, come from the electromagnetic field. And even when no particles are present, these fields are never completely quiet. They're always fluctuating, producing tiny, short-lived particles that appear and disappear like cosmic fireflies. This restless energy in so-called empty space is known as vacuum energy. Think of it like the surface of a pond. From a distance, it looks smooth and still. But if you get closer, you'll notice ripples, little disturbances, maybe even a fish jumping here and there. What seems calm and featureless from far away is actually full of hidden motion. That's why physicists say the vacuum isn't empty. It's full of potential. Particles pop in and out of existence in fleeting pairs. These are called virtual particles. We can't see them directly, but we can measure their effects. For instance, they influence how electrons behave around atomic nuclei, and they even play a role in one of the biggest mysteries in physics: dark energy. Dark energy is the strange force that seems to be pushing the universe apart, faster and faster, and vacuum energy might be part of the reason why. So no, space isn't just that mysterious place where your keys disappear or where your thoughts drift off during awkward moments. It's full of structure and motion, even when there's nothing visible to the eye. And here's where things get even stranger. Space itself can expand, not just the objects inside it moving farther apart, but the actual space between them stretching out. That idea also comes from Einstein's theories, and it's a key part of how we understand the universe today. Let's pause for a second. It's easy to feel overwhelmed by the thought that the emptiest thing in existence is actually buzzing with energy, geometry, and invisible fields. But in a way that makes it more comforting, because it means the universe isn't just a cold, empty void. Even in its quietest, darkest corners, something is always happening. There's a soft background hum, like the gentle crackle of a fireplace, or the rustling of leaves on a still night. That hum, those tiny fluctuations, that restless vacuum, they're all reminders that space isn't just the absence of stuff. It's a real physical thing with its own properties. It can bend, it can stretch, it can expand and ripple. It has energy, it even has temperature. In fact, the vast emptiness between galaxies is believed to be just a few degrees above absolute zero, still faintly warmed by the leftover glow from the Big Bang. So when we ask about what is space, we're not talking about a blank nothingness. We're talking about a rich, structured fabric that connects every atom, every galaxy, every living being. Space isn't just where things happen. Space is one of the things that happens. It's part of the story, not just the stage. And maybe that's the strangest part. The more we study space, the more it refuses to be empty. It bends, it hums, it fluctuates, it expands. Even when it seems like nothing's going on, it's never truly still. And as for those missing socks, space probably isn't the culprit. But if they did somehow slip into a warped pocket of space-time, well, they'd be part of a very exclusive scientific mystery. Now picture yourself standing on a quiet hilltop under a clear night sky, looking up at a universe that stretches out in every direction. It feels endless, infinite, eternal. But what if I told you there's actually a limit to how far we can see? A kind of cosmic bubble that surrounds us, not because the universe ends there, but because light from beyond simply hasn't had time to reach us yet. This isn't science fiction. It's what scientists call the observable universe. It's the part of the cosmos we can actually detect. Light, radiation, gravitational waves, anything that's managed to travel to us since the beginning of time. That word observable is important. It doesn't mean there's nothing beyond it. It just means we haven't seen it yet. Now here's where things get really interesting. You might think that the farthest we could possibly see would be about 13.8 billion light-years away. After all, that's roughly how long the universe has existed, give or take a few 100 million years. And since light travels at, well, the speed of light, wouldn't that be the edge of our vision? How if only the universe were that simple? Because of the way space itself expands, that boundary, the edge of what we can see, is actually much farther out than you might expect. The observable universe has a current radius of about 46.5 billion light-years in every direction. That means it's roughly 93 billion light-years across. Yes, you heard that right. Even though the universe is only about 13.8 billion years old, the farthest galaxies we can detect are more than 3 times that distance away. Why? Because space has been stretching the entire time. Here's a simple way to picture it. Imagine placing raisins on a loaf of bread and putting it in the oven. As the bread rises, the raisins move farther apart. Now imagine a photon of light is sent from one raisin to another, just as the baking begins. By the time that light reaches its destination, the bread has expanded. The light didn't travel across a fixed distance, it traveled across a growing one. The target moved farther away while the light was still on its way. That's more or less what happens on the cosmic scale. This brings us to something called the cosmic horizon. It's not a wall. You won't fly a spaceship out there and suddenly bump into the edge of the universe like in a cartoon. It's more like a gentle fade-out of information. Beyond this horizon, light from those far-off regions hasn't had enough time to reach us since the Big Bang. It's like standing in a vast fog. You can see the glow nearby, but everything beyond is hidden. Not because it doesn't exist, but because the universe hasn't sent us the signal yet. This horizon marks the boundary of our observable universe. And it's not fixed, it's always changing. As time passes, light from more distant places will eventually reach us, and our bubble of visibility will grow. But here's the twist. Because space is expanding faster and faster, some galaxies are moving away from us so quickly that the light they emit today will never reach us, not even in trillions of years. They're receding faster than light, not because they're breaking any cosmic speed limit, but because the space between us is stretching too fast. In a very real way, parts of the universe are slipping out of our reach. Now let's take a quiet moment to appreciate something beautiful. Every star, every galaxy, every faint smudge of light we see in the night sky, that's all within our observable universe. That's the good news. The not-so-good news? There's almost certainly much more beyond it, maybe even infinitely more, and we'll never be able to see, touch, or study it. We're surrounded by a vastness that goes far beyond what our instruments can detect. And here's something even more humbling. Every person, everywhere in the universe, has their own observable universe. If you were standing on a galaxy 10 billion light-years away, your view of the universe, your cosmic bubble, would overlap with ours a little. But it would also include regions we'll never be able to see. That's because the observable universe isn't the whole universe. It's just our slice of it. And what a slice it is. Scientists estimate there are roughly 2 trillion galaxies within our observable bubble. Each one holds millions to trillions of stars. That's a lot of starlight packed into our little window of the cosmos. The photons from some of those galaxies have been traveling for billions of years, just to reach the back of your eye or the sensor in a telescope. Some of that light began its journey before Earth even existed. That ancient glow is like a time machine, a message from a distant past. And yet, as rich and full as our observable universe is, it might only be a tiny part of the whole picture. Beyond the cosmic horizon, space might go on forever. There it could be curved, flat, or loop back on itself in ways we can't imagine, maybe even involving extra dimensions. But we'll never know for sure. Not with light. Not with any signal that's limited by time and the speed of causality. There's a kind of peace in that limit. Knowing we can't see everything reminds us that our place in the universe is local. We don't need to understand or control the entire cosmos to find meaning in it. Sometimes it's enough just to sit under the stars and know you're part of something much bigger than yourself. And while 93 billion light-years sounds enormous, and it is, it's also just the visible frosting on a cosmic cake that's far bigger than we can ever taste. What lies beyond? We can only guess. Maybe more galaxies, more structure, more dark matter and dark energy, or maybe something stranger. But for now, we're here, floating inside a glowing bubble of light, information, and time. A bubble shaped not by borders, but by the patient journey of photons and the limits of cosmic time. It's not a prison. It's a gift, a slowly expanding gift that lets us see deeper into the story of the universe with every passing day. When we look up at the night sky, we often think we're seeing the universe as it is right now, but that's not quite true. What we're really seeing is the universe as it was. Every star, every galaxy, every glowing dot in the sky is a time capsule. The farther away it is, the older the light we're seeing. In fact, looking across the universe is a bit like rummaging through a cosmic attic. Each layer of light takes us deeper into the past. Let's start with the basics, the light year. A light year is the distance light travels in 1 year, about 6 trillion miles, or nearly 10 trillion kilometers. So when you look at a star that's 100 light years away, the light reaching your eyes left that star 100 years ago. You're seeing it not as it is now, but as it was when your great-grandparents were still young. Now stretch that idea across the vastness of space. Some of the galaxies we observe are billions of light years away. That means the light we're detecting from them began its journey before our solar system even existed. Long before Earth had oceans or life, that light was already racing toward a future observer, toward you. This brings us to a concept astronomers call look-back time. It's a way of describing how far into the past we're seeing when we observe distant objects. If a galaxy is 8 billion light-years away, its look-back time is 8 billion years. That light has been traveling across space for more than half the age of the universe, arriving just in time to brighten your evening stargazing or to hit the mirrors of a telescope orbiting Earth. In a strange way, space is full of ghosts, echoes, of what once was. We're not seeing galaxies as they are today. We're seeing them frozen in earlier chapters of their lives. Some of them may not even exist anymore. They might have merged with other galaxies, changed shape, run out of star-forming gas, or drifted beyond the reach of light due to the expansion of space. What we see is a kind of cosmic fossil record, written in photons, and it gets even more fascinating. As light travels through the expanding universe, it stretches. This effect is called redshift. Just like the pitch of an ambulance siren drops as it moves away from you, the wavelength of light gets longer when its source moves away. Since space itself is expanding, nearly all distant galaxies are moving away from us. And the light they emit gets stretched into longer, redder wavelengths as it travels. That's why it's called redshift. By measuring how much redshift is in the light from a galaxy, astronomers can figure out how far away it is and how long that light has been traveling. A high redshift means a very distant galaxy and a very ancient glimpse into the early universe. This redshifted light holds clues about the structure, age, and history of the cosmos. It tells us how fast the universe is expanding, how galaxies change over time, and even hints at mysterious forces like dark energy that shape everything on a massive scale. Every color-shifted photon is a little messenger from the past, carrying encoded stories about where it came from and what the universe was like back then. Now let's talk about telescopes, our cosmic time machines. When you look through a telescope, you're not just seeing things more clearly, you're seeing them deeper into time. A backyard telescope might show you Jupiter's clouds from about 40 minutes ago. A more powerful observatory could reveal a galaxy as it looked 500 million years in the past, back when life on Earth was still experimenting with fins and gills. Then we have the heavyweights, the great observatories like Hubble, James Webb, and the future telescopes still in development. These instruments can peer so far into space and so far back in time that they capture the faint light from the very first galaxies to ever form. We're talking about structures that began taking shape just a few 100 million years after the Big Bang. It's a bit ironic that in trying to understand the future of the universe, we spend most of our time looking into its past. But that's just how light works. It moves fast, but not instantly. And since the universe is so enormous, even light has a hard time keeping up. That means the universe, as we experience it, is always slightly behind the times. It's like watching a movie that's still being edited, scenes arriving one by one out of order, some from galaxies nearby, others from across the cosmic deep. Still, that delay is a gift. Without it, we wouldn't be able to piece together the story of how everything came to be. The slow arrival of ancient light lets us see different stages of the universe's evolution all at once, like scattered pages from a book spread across the sky. The result is a kind of beautiful patchwork of time. In one direction, we might see a galaxy that formed fairly recently. In another, we might catch a flicker of light from billions of years ago, when stars were just beginning to form. From clouds of early gas. All these images are layered not just across space, but across time itself. You could say we're living inside a museum made entirely of light, but instead of walking from one exhibit to the next, we let the photons come to us, crossing vast distances to share their stories, filling our sky with ancient news from the dawn of everything. There's something quietly powerful about the idea that every time you look up, you're looking into a time machine, that the light touching your eyes may have started its journey before the first tree grew on Earth, before the first cell formed, before the atmosphere even existed. And all of this, all these insights, come from simply paying attention to light. By studying its colors, its shifts, and its age, we unlock a silent language spoken across billions of years, a language that doesn't just describe the universe, it is the universe encoded in motion and memory. Next time you see a star twinkling above, remember, you're not seeing it as it is. You're seeing a version of it preserved in time, a glimmer of history still traveling through the dark. You're seeing what the universe looked like when it was younger, smaller, maybe even gentler, and through science and with the steady help of light, we keep building our origin story, one distant glow at a time. Now picture yourself standing in a field early in the morning. The grass is damp with dew. The air is cool. A soft fog rolls across the horizon. You can only see a short distance ahead, maybe a few trees, the outline of a hill, but beyond that, everything fades into a pale blur. You know the world continues, past the fog, but your eyes can't reach it yet. In a way, that's what it's like to live inside the universe. No matter how advanced our telescopes become, there's a limit to how far we can see. Not because of fog in the usual sense, but because of time, distance, and the strange nature of the expanding cosmos. These limits are called cosmic horizons. They define the edges of our observable universe. Unlike the neat horizon on Earth, where the sky meets the land, cosmic horizons come in different types, each with its own meaning and rules. The first is called the particle horizon. Think of it as the farthest distance from which light or any signal could have reached us since the universe began. It marks the outer edge of what we can currently observe, the limit of our cosmic bubble. The particle horizon is shaped by time. Since the universe has existed for about 13.8 billion years, and space has been expanding during that time, the furthest distance light could have traveled to reach us today is around 46 billion light-years in any direction. That's why the observable universe is roughly 93 billion light-years across. It's the grand perimeter of everything we can detect right now. But don't think of this horizon as a wall. There's no border, no glowing edge with a no-entry sign. It's a limit built into time itself. Like standing on the shore of a vast ocean, you can look out as far as the light allows, but you won't see beyond that gentle curve. Not because there's nothing there, but because the signals haven't had time to arrive. Next, we have the event horizon of the universe, not to be confused with the dramatic kind around black holes. In cosmology, the event horizon is the boundary beyond which events can never affect us, no matter how long we wait. It's the cosmic line in the sand. Anything beyond this point is moving away from us faster than the speed of light because of space expansion. That light, no matter how determined, will never catch up to us. It's a bit like trying to send a message to a friend floating away on a raft down a river. You toss a bottle with a note inside, but the current is so strong that the raft drifts faster than the bottle can reach it. No matter how hard you try, the message will never reach its destination. That's the event horizon, where communication, even light itself, becomes impossible. Right now, scientists estimate the cosmic event horizon sits about 16 billion light-years away. That means there are parts of the universe we can still see today. But if those regions send out new light now, it will never reach us. We're watching galaxies that are, in a very real sense, slipping away. Visible for now, but destined to fade from view forever. Then there's the cosmological horizon. Sometimes it's used interchangeably with the particle horizon, but it can also refer to broader boundaries in spacetime. It's a term that captures these observational limits and reminds us that horizons aren't just about what we can see, they're deeply connected to the physics of the universe itself. You can think of the cosmological horizon as the moving edge of what we can observe. It expands outward as time passes, and light from more distant places finally reaches us. These horizons are always shifting. As the universe gets older, the particle horizon grows, more light has time to arrive. But because of dark energy and the accelerating expansion of space, the event horizon becomes more limiting. More galaxies slip beyond our reach. The universe becomes more isolated, not because it's empty, but because the light from its farthest corners can't keep up. To picture it another way, imagine the universe as a slowly inflating balloon. Dots on the surface drift apart, and the farther they are, the faster they move away. We can only see the dots close enough for their light to reach us. Beyond that, the light stretches and fades until it disappears into the expanding void. There's something haunting yet peaceful about these limits. They quietly remind us that we're not all-seeing observers. Our view is shaped by cosmic history, by how long light has been traveling, and by the strange nature of the space it moves through. We're looking through a window that's vast, yes, but still finite. Some parts of the universe will always remain unknown, no matter how clever or patient we are. Not because our tools aren't good enough, but because of the very structure of space-time. These unreachable regions aren't hiding behind a curtain waiting to be revealed. They're beyond the reach of information, forever out of bounds. And yet, even within these limits, we've learned so much. We've mapped galaxies, measured background radiation, and traced the fingerprints of the Big Bang. We've used the haze of the particle horizon to understand the universe's structure, and the glow of ancient light to piece together its history. Horizons don't restrict our imagination, they shape it. Like the sun burning away morning fog, each new discovery pushes the haze back a little more, revealing more of the cosmic landscape. But some parts will always stay hidden, beyond the curve, beyond the stretching boundary where light will never arrive. Still, here we are, spinning quietly in one corner of the universe, watching photons arrive from billions of years ago, reading the messages they carry, and wondering what lies beyond the next gentle bend in the cosmic road. Even if we can't see everything, even if parts of the universe are forever unreachable, there's beauty in the effort. In listening to the quiet hum of light, in following it to the edge of knowledge, and in knowing that even without the full picture, we're part of the story. Not too long ago, in the grand timeline of human curiosity, people thought the universe was pretty steady. Galaxies were out there, stars were shining, and everything more or less stayed in place. A quiet, eternal cosmos. But in the early 20th century, a discovery from a mountaintop observatory changed everything. And the universe hasn't stood still since. It was Edwin Hubble, yes, the same name as the famous space telescope, who noticed something unusual. While studying distant galaxies, he found that their light was consistently redshifted. That meant they were moving away from us. And the farther away they were, the faster they seemed to recede. This wasn't a random trend or a coincidence. It was a pattern, a law. Space itself, it turned out, was expanding. Now, this doesn't mean galaxies are racing through a fixed space like cosmic race cars. They're not bursting outward into some empty void. What's happening is stranger and more elegant. Space itself is growing. Imagine space as the thing that's stretching, and galaxies are being carried along with it, like raisins in a rising loaf of bread. That image, raisin bread, is a simple and surprisingly accurate way to picture it. Think of the dough as space and the raisins as galaxies. As the dough rises, it stretches in every direction. Each raisin ends up farther from the others, not because it's moving on its own, but because the dough between them is expanding. There's no central raisin, no preferred direction, just a uniformly growing loaf. This is how the universe behaves, on a large scale. Galaxies aren't flying through space like cannonballs. They're being pulled apart as the fabric of space itself stretches. That's why, no matter where you are in the universe, it looks like everything else is moving away from you. From every galaxy's perspective, space is expanding in all directions. It's a bit like being inside a rising bubble. No matter which bubble you're in, all the others seem to drift away. The universe isn't expanding into anything, it's just expanding. There's no outer shell, no edge it's racing toward. Instead, the distances between unbound objects grow over time, like a cosmic measuring tape slowly stretching. This idea of an expanding universe was so radical when Hubble introduced it that even Albert Einstein had to revisit his own equations. Originally, Einstein had added something called the cosmological constant to his general theory of relativity to make the universe stay still. He believed the cosmos had to be static, But left alone, his equations suggested otherwise. It's not that the galaxies are moving too fast. It's that the space between us is working against the light trying to reach us. In some parts of the universe, especially those very far away, space is expanding so quickly that light can't make progress toward us. It's like paddling a canoe upstream during a flash flood. The current is too strong, and your boat gets swept farther away no matter how hard you try. This doesn't break the rules of relativity. That theory only says objects can't move through space faster than light. It doesn't say anything about how fast space itself is allowed to grow. And as it turns out, space has a flair for dramatic growth. Take the period known as cosmic inflation. It was a mind-bendingly brief moment, just after the Big Bang, when the universe expanded at an astonishing rate, much faster than the speed of light. In less than a trillionth of a second, the universe grew from something smaller than a proton to something the size of a grapefruit, or maybe even bigger. Try putting that kind of expansion into a recipe, and again, this faster-than-light growth didn't break any laws. It was space itself doing the expanding, not particles racing through it. It's one of the rare cases in physics where faster-than-light travel isn't just allowed, it's expected. Just don't try it in a spaceship. Your engines won't be thrilled. This rapid inflation smoothed out the early universe, ironing out wrinkles and uneven spots like a cosmic steam press. It also helps explain why the universe looks so uniform in every direction. Even though distant regions haven't had time to exchange signals, inflation spread everything out so fast that local differences became subtle and far apart. Even now, billions of years later, we're still seeing the effects of that expansion. Space keeps growing, pulling distant galaxies farther and farther away. Some of those galaxies are now receding faster than light, not because they're speeding up, but because the space between us is expanding faster than light can close the gap. That means there are parts of the universe we'll never see. No matter how long we wait, their light won't reach us. And if they send out new light today, it'll be swept away into the deepening void. These galaxies aren't lost because they're moving too fast. They're lost because the road between us is stretching faster than their signals can travel. It's like trying to send a postcard across a river where the opposite shore is drifting away faster than you can throw. No matter how many stamps you use, the postcard won't make it. Eventually, even the idea of delivery stops making sense. So when astronomers say some galaxies are receding faster than light, here's what they mean. Because space is expanding, the distance between us and those galaxies is increasing faster than light can travel. There's no rule breaking, no strange loophole, just a clever twist in how space and time behave. And this cosmic trick leads to another strange result. There are galaxies we can still see today, clear as ever through our best telescopes, that have already crossed this horizon. We're seeing them because the light they emitted long ago is still arriving. But the new light they're producing now, that's already out of reach. It will never get here, not even if we wait forever. It's like watching the tail lights of a car that just turned a corner. You can still see the glow, but the car itself is gone, driving down a road you'll never follow. The light is a ghost, a message from a past that can't be updated. There's a quiet sadness to this reality. The universe is full of stories we'll never hear, stars we'll never see, galaxies we'll never know existed. Not because we didn't try hard enough, but because the cosmos itself is stretching the stage beyond our view. And yet that's part of the wonder. The fact that we've glimpsed so much of the universe's past is nothing short of amazing. Despite all the distance and distortion, we've managed to see billions of light years in every direction. We've caught ancient photons mid-flight, traced the birth of galaxies, and even detected the faint afterglow of the Big Bang. And all of this has happened from a small planet orbiting a fairly average star in a typical galaxy, in a universe where space moves faster than light. It's enough to make you feel small, but also incredibly lucky, because here we are, listening to the whispers of an expanding cosmos, watching light struggle to reach us, counting galaxies as they fade into the distance. And all the while, the dough of the universe keeps rising, carrying with it the dreams of curious beings who once wondered how far light could go. When we think about the universe, it's easy to picture it like a giant black box, A huge rectangular space with a top and bottom, left and right, front and back, just floating in something. Maybe it has edges. Maybe it goes on forever. Maybe there's a giant cosmic wall with a "Do Not Enter" sign and a very bored security guard, but the actual shape of space is much more subtle and far more interesting. Space isn't necessarily flat like a tabletop. It might be curved. In fact, it could be positively curved, negatively curved, or just barely flat. And this isn't just about how it looks. The geometry of the universe affects how it evolved, how it behaves, and whether it might one day curve back in on itself or keep stretching forever. Let's start with the three main possibilities. The first is a flat universe, like an infinite sheet of paper. In this model, geometry works just like we learned in school. Parallel lines never meet. Triangles always add up to 180 degrees, and if you travel in a straight line, you'll never loop around. You'll just keep going forever through an endless cosmic plane. The second option is a closed universe, shaped like a sphere, or more precisely, the three-dimensional version of a sphere. In this model, space curves back on itself. If you were to head off in a straight line in any direction, avoiding stars, planets, and all the other cosmic clutter, you'd eventually end up right back where you started. Just like walking straight across Earth's surface, you wouldn't fall off. You'd keep going in circles, though it might take several billion years and a seriously durable pair of shoes. The third possibility is an open universe, shaped like a saddle. This kind of space curves outward. Think of a Pringle. In this geometry, parallel lines eventually drift apart. Triangles add up to less than 180 degrees, and if you tried to loop around the universe, you'd never return to your starting point. You'd just keep drifting farther and farther into the cosmic vastness. These shapes, flat, closed, and open, aren't just abstract ideas. They're directly tied to the universe's overall density and energy content. Specifically, how much matter and energy exist compared to what would be needed to make the universe perfectly balanced. This critical density determines whether space bends inward, outward, or not at all. If the actual density is greater than the critical density, space is closed and positively curved. If the density is lower, it's open and negatively curved. And if the densities match just right, the universe is flat. It's a bit like the Goldilocks zone of cosmology. Not too much, not too little, but just enough to keep the geometry straight. So, how do we measure this? Turns out the universe leaves behind clues in the cosmic microwave background, the ancient light that's been traveling since shortly after the Big Bang. By studying the tiny fluctuations in this faint glow, scientists can figure out how space bends light over huge distances. It's like using ripples on a pond to understand the shape of the shoreline. So far, the evidence points to something remarkable. Our universe appears to be very, very close to flat. Not perfectly flat, maybe, but close enough that any curvature is too small to detect with today's instruments. It's like standing on a massive plane that might have a slight bend somewhere far off, but as far as you can see, it looks pretty straight. Now here's where things get really interesting. A flat universe can still be infinite, or not. And a closed universe, surprisingly, can be finite but without edges. That phrase might sound like a contradiction at first, like saying you have a mug that's full but holds no coffee. But it makes sense with a little thought. Take the surface of a sphere. It's finite, you can measure its total area, but it has no edges. You can walk around a globe forever and never fall off, because there's no edge to fall from. The whole surface loops back on itself. Now apply that idea to a three-dimensional version. That's what cosmologists mean when they say space can be finite but unbounded. It's a closed loop, a self-contained bubble of geometry. This kind of space doesn't have a border. There's no spot where the universe ends and something else begins. It's just space curving back around in a grand, subtle loop. And because we live inside it, we'd never be able to tell directly. We just keep drifting forward thinking we're going straight, while quietly bending back toward where we started. Even in a flat or open universe, infinity brings its own strange flavor. An infinite universe means an endless number of galaxies, stars, and maybe even repeating patterns. Somewhere out there, if the universe really is infinite, there could be another version of you watching this same video, maybe in a slightly different pair of pajamas. Now, it's important to remember that we can only observe a small part of the universe, just what's inside our observable horizon. We don't know how space behaves beyond that. It could stay flat forever, or it could curve into a loop that's too subtle for us to detect. Might be so gentle that even a beam of light traveling for billions of years wouldn't reveal it. It's like trying to tell if Earth is round while standing in a meadow. You don't see the curve, but it's there. Cosmic geometry also affects the future of the universe. In a closed universe, gravity might eventually slow down the expansion and cause everything to collapse, leading to a big crunch. In an open or flat universe, expansion could go on forever, thinning out matter and cooling everything into a quiet fade. But with dark energy pushing things apart faster and faster, the big crunch seems unlikely, at least based on what we know today. What's quietly comforting in its own way is that no matter what shape the universe takes, we're part of it. Whether the universe loops or stretches, curves or drifts, we're woven into its structure. Our atoms follow its geometry. Our light traces its curves. Our thoughts echo through its halls. We don't just live in space. We are space, folded into itself in a dance of mass and motion. So if the universe is flat, we're living on a vast plane of cosmic possibility. If it's curved like a sphere, we might be looping around inside an invisible bubble. If it's open, we're gliding across an endless saddle, heading out into infinity with no return trip planned. Whichever version turns out to be true, it's strange, elegant, and just confusing enough to be beautiful. And that's part of the magic. You don't need to pin down the shape of space to appreciate its mystery. You can simply look up, smile at the stars, and know you're standing on a tiny patch of something grand and endlessly curious. We live in a universe with a shape we're still trying to picture from the inside out. So imagine you're a tiny creature walking along the surface of a balloon. You can move north, south, east, and west, but you can't dig down or float above. Your entire world is that two-dimensional skin, curved, smooth, and continuous. You don't know the balloon is being held by a giant cosmic toddler with a helium tank. You just know that if you walk straight long enough, you'll eventually end up back where you started. That's the magic of curved space. It follows rules that don't always match our everyday experience, and yet once you get used to it, it makes perfect sense. While we humans live in 3 dimensions of space, curved surfaces in 2 dimensions give us a surprisingly helpful way to imagine what our universe might be doing on a much larger scale. Let's begin with something simple. On a flat surface, like a sheet of paper or a smooth tabletop, geometry behaves in familiar ways. Draw a triangle and the angles will always add up to 180 degrees. Draw 2 parallel lines and they'll never meet. Walk in a straight line and you'll keep going forever, unless you hit a wall or a spilled cup of coffee. Now imagine walking on the surface of a sphere, like a planet or that balloon we mentioned earlier. Geometry starts to behave differently. If you draw a triangle using great circles, like the equator and lines of longitude, the angles can add up to more than 180 degrees. Parallel lines don't stay parallel. They meet at the poles or drift apart depending on your path. Most importantly, if you walk in a straight line on this curved surface, you'll eventually return to your starting point without ever turning around. No edges, no borders, just a smooth loop. From your limited view on the surface, space feels infinite, but in reality it's finite and curved back on itself. Now scale that idea up. Imagine our entire universe as a 3-dimensional version of that balloon surface, except instead of curving in 2 dimensions, it's curving in 3, or more accurately, in a way we can't easily picture, because it curves in higher dimensional space. You and I live inside this 3-dimensional space, moving through it, without ever seeing the outside, just like the balloon creature never sees the air around the balloon. In this analogy, galaxies are like dots drawn on the balloon's surface. As the balloon inflates, the dots move farther apart, not because they're crawling across the surface, but because the surface itself is stretching. That's what cosmologists mean when they say the universe is expanding. Galaxies aren't flying through space like comets on vacation. Space itself is growing, and galaxies are being carried along with it. And just like our balloon creature, if the universe is truly curved and finite, then traveling in a straight line long enough might eventually bring you back to where you started. You wouldn't fall off the edge of space because there is no edge. The loop closes smoothly. It's a finite space with no boundary. Her strange and beautiful idea. You could go on an endless journey through a finite universe, never hitting a wall, never running out of room. The balloon analogy also helps explain something else, why there's no special center of the universe. Just as there's no single center on the surface of a balloon, the universe doesn't have a central point from which everything is expanding. Expansion happens everywhere at once. Every point on the balloon moves away from every other point as it inflates. You could pick any spot and call it here, and the view would look the same in all directions. It's worth pausing to say that the balloon analogy isn't perfect. It's just a model to help our three-dimensional minds grasp a higher dimensional idea. The balloon's surface is two-dimensional and sits in three-dimensional space, which we can see and imagine. But if our universe is curved, it might be curved in a higher dimensional space we can't observe directly. It's not floating in a bigger container. Space doesn't need an outside to curve. It can curve on its own, based on its internal properties. This idea of intrinsic curvature is one of the key insights from Einstein's theory of general relativity. Space, and space-time more broadly, isn't just a passive backdrop. It has shape and structure, and that shape can change over time. Mass and energy tells space-time how to curve, and the curvature of space-time tells matter how to move. It's a beautifully circular relationship, one that governs everything from the orbits of planets to the behavior of galaxies on the largest scales. The curvature of space also affects how light travels. In curved space, light doesn't move in straight lines the way we usually think. It follows the shortest possible path, called a geodesic. On a sphere, that's a great circle. In our universe, it's a curved path shaped by gravity and the structure of space itself. That's why massive objects like stars and black holes can bend light, a phenomenon known as gravitational lensing. So when we look up at the night sky, we're not just seeing objects scattered across flat, empty space. We're seeing a web of light moving through curved space, stretched, bent, and shaped by the mass of everything around it. It's like looking at the stars through a slow-moving funhouse mirror, except the distortions reveal something real about the shape of the universe. Let's return to our balloon one last time. As it expands, the space between galaxies on its surface increases, but the galaxies themselves don't stretch. They stay the same size. That's because space expands on large scales, between objects that aren't held together by gravity. So our Milky Way, our solar system, even Earth and its well-worn coffee shops, none of those are being pulled apart like taffy. Expansion only takes hold in the vast emptiness between galaxies. And what's causing this expansion? Scientists now believe it's driven by dark energy, a mysterious form of energy built into space itself. It's causing the universe to grow faster and faster, like a balloon that not only inflates, but does so more rapidly with each breath. We don't yet know what dark energy actually is, but we can see its influence in how distant galaxies move and how ancient light spreads across the sky. So where does that leave us? It means we live in a space that might be curved, might be finite but without edges, expanding without a center, and shaped by rules that feel unfamiliar but make sense in the grand cosmic rhythm. And all of this, the curves, the expansion, the possibility of looping back to where we began, can be imagined with a simple balloon. A stretchy metaphor floating through thought, whispering quiet truths about a universe that grows not outward from something, but within itself. Next time you see a balloon rising into the sky, give it a little nod. It may be full of helium and squeaky fun, but it also carries the shape of something far greater. A gentle curve, a stretch of space, and the quiet idea that maybe, just maybe, the place you're heading is also the place you started. Only now you've traveled the universe to get there. Infinity. Just saying the word feels like it should echo. It's vast, mysterious, and a little intimidating. It brings to mind endless stars, limitless space, and math problems that make high school students rethink their choices. But what does it really mean when we ask, is the universe infinite? Does space truly go on forever without a final edge or wall, or is something more subtle happening? Let's begin with what we do know. So far, everything we've measured about the large-scale structure of the universe suggests it might be infinite. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, show that space is extremely close to flat, not curved like a sphere, not shaped like a saddle, just flat, in a geometric sense. And in general relativity, a flat universe could very well be infinite. If it's not, then it's at least far larger than the part we can observe. That brings us to the observable universe, the cosmic bubble we can actually see. It stretches about 93 billion light-years across. That's the portion of space we have access to, because light from those regions has had time to reach us since the beginning of the universe. But beyond that, it could keep going. There might be more galaxies, more cosmic structures, entire regions of space we'll never detect, places that are forever beyond our reach. And here's the catch. We can't prove or disprove whether the universe is infinite. We're limited by what we can observe. We're like ants on a beach, looking in every direction and seeing only sand. For all we know, the beach stretches across the continent, or maybe it ends just past the next dune in a tide pool full of curious crabs. We simply can't see far enough to know. This brings up an important point. We don't measure infinity, like we measure the distance to the moon. You can't stick a ruler on space and keep going until the numbers stop. Infinity isn't a number, it's a concept. And in science, concepts need evidence. That's where things get tricky. You can't directly observe infinity. You can only look for signs that space doesn't curve back on itself, doesn't end abruptly, and doesn't behave in a way that suggests it loops. So far, we've looked in every direction and found no edge, no sudden drop-off, no cosmic fence with a do not pass sign. But that doesn't mean such a thing doesn't exist. It just means it's beyond what we can see. And unless someone invents a telescope that can break the speed of light and outrun the expansion of space, that's not going to change anytime soon. The idea of an infinite universe comes with some strange consequences. If space is truly infinite, then the amount of matter it contains is also likely infinite, or at least so enormous it might as well be. That means endless stars, planets, comets, clouds of dust, and yes, maybe even life. Somewhere out there, in the farthest reaches of a never-ending cosmos, there could be another planet like Earth. Maybe it has trees that grow sideways. Maybe its oceans shimmer with unusual colors. Maybe it has beings asking the same questions we are, wondering whether their universe ever ends. And here's where things get mind-bending. In an infinite universe, if matter is spread out more or less evenly, then probability suggests patterns will eventually repeat, which means somewhere out there could be a version of you or several. Some might be nearly identical. Others might have picked a different breakfast cereal this morning and accidentally changed the course of their entire day. Don't worry, this isn't meant to be unsettling. You're not going to run into your cosmic twin at the grocery store. These regions are likely so far away, they'll remain unreachable forever. The light from those distant parts of space will never reach us, not even if we waited longer than the age of the universe multiplied by every grain of sand on Earth. Still, the idea carries weight. Infinity isn't just about size. It's a shift in how we think. It turns the universe from something big into something without limits. You don't have to ask what's beyond the edge of the map, because there is no edge, just more map stretching endlessly. Of course, scientists have good reasons to be cautious about assuming the universe is infinite. We only have a limited sample to study. Cosmologists still consider the possibility that space might be very large, but still finite. It could curve gently back on itself in ways we haven't detected yet, looping through higher dimensions or forming a shape stranger than anything we've imagined. There's also the matter of time. The universe might be infinite in space, but not in duration. It had a beginning, what we call the Big Bang, and while the idea of a beginning is complex, it suggests that even if the cosmos stretches endlessly, it hasn't always existed in its current form. Philosophically, infinity challenges how we relate to the universe. Most things in our lives have limits, our time, our energy, the number of cookies in the jar. Infinity breaks that pattern. It removes the edges and opens up a playground of endless possibilities, something that can feel inspiring, overwhelming, or both. Some ancient thinkers were uncomfortable with the idea. Aristotle, for example, believed the universe must be finite because actual infinities were too strange to accept. Even today, scientists and philosophers debate whether true infinities exist in reality or are just helpful concepts. But whether the universe is infinite or not, thinking about it still matters. It stretches our minds, encourages humility, and reminds us how limited our perspective really is. When you look up at the stars, you're staring into a mystery so vast that even our boldest measurements barely scratch the surface. You're seeing a local glow, a few lights in the windows of a cosmic mansion, and yet here we are, tiny beings on a spinning planet, wondering how far space goes. We build tools to chase ancient light. We invent math to describe the impossible. We lie awake at night thinking about what's beyond the last star we can see. Maybe the universe is infinite. Maybe it's not. Either way, it's more than enough to fuel our questions, our stories, our science, and our dreams. More than enough to remind us that we're part of something truly vast. And the best part? You don't need to know how far it goes to feel at home in it. You're already part of its fabric, a flicker of thought on the edge of the observable, glowing quietly in a cosmos that may never end. There's something deeply compelling about the idea of an edge. We grow up surrounded by edges, walls, fences, sidewalks, lunchboxes. Everything we know seems to stop somewhere. So when we think about the universe, it's natural to imagine it must stop too. Surely after some unimaginable distance, space must come to an end, like the final room in a massive mansion or the edge of a giant tabletop hanging over the void. But here's the twist. Space doesn't need an edge. It can be finite in size, without having a boundary, and that's where things get beautifully strange. Let's start with something familiar. Picture the surface of Earth. If you walk in a straight line in any direction, you'll eventually circle back to where you started. You won't fall off. You won't hit a wall. And you won't find a sign that says, "End of Earth, please turn around." The surface is finite but unbounded. It loops back on itself smoothly. Now take that idea and apply it to three-dimensional space. Imagine living inside a volume that wraps around itself, just like Earth's surface does in 2 dimensions. If you kept moving forward in a perfectly straight line, you might eventually return to your starting point, without ever hitting a wall, cliff, or edge. This kind of space isn't science fiction. It's a valid model in cosmology. It's called finite unbounded space. It sounds like a contradiction, like saying a cup is full of tea but doesn't contain any liquid. But once you understand the geometry, it makes sense. Space can be shaped so that it closes in on itself, forming a complete volume without needing to end. One classic shape used to explain this is the torus. Think of a donut, not the jelly-filled kind, but the smooth, round kind with a hole in the middle. The surface of the donut is 2-dimensional. You can walk around it without leaving the surface, and it has no edges. It loops back on itself both horizontally and vertically. If you're an ant walking on the donut, you can keep going, forever without hitting a boundary. Now imagine a 3-dimensional version of that, where space loops in multiple directions. This doesn't mean the universe is shaped like a pastry, but the torus helps us picture how space might behave if it were finite and without borders. You could start at one point in space, travel in a straight line, and after a very, very long time, end up back where you started, like a galactic boomerang. Another helpful analogy comes from video games. In some classic arcade games like Pac-Man or Asteroids, if you move your character off one edge of the screen, they reappear on the opposite side. It's not that there's a hidden tunnel. They've just looped around on a map that wraps back on itself. These are 2-dimensional versions of a toroidal space. The game world is finite in size, but the edges don't behave like real-world walls. They connect. In theoretical cosmology, this idea isn't just playful speculation. Some models suggest the universe could have a topology, a fundamental shape that loops back in subtle ways. We might not notice these loops unless we looked far enough and in just the right direction. There's even been speculation that if the universe is small and curved just right, we might detect repeated patterns in the cosmic microwave background, like mirrored wallpaper left over from the Big Bang. So far, no clear signs of this repetition have been found, but the possibility hasn't been ruled out. The deeper truth is that the universe doesn't need an outer surface or a surrounding void. That's a very human way of thinking, something sitting inside something else. But space isn't a thing embedded in a bigger thing. It is the thing. It's not like a balloon floating in the air. It's more like the entire balloon itself, with all of us stuck on its surface, unable to step outside and look in. Even if the universe is infinite, it doesn't require an edge. Infinity isn't a location, it's a property. Saying the universe is infinite is like saying numbers never end. You don't need to find the last number to know it doesn't exist. Likewise, you don't need to locate the edge of space to accept that there might not be one. Edges also create philosophical puzzles. If there were an edge, what would lie beyond it? More space, something else entirely. A blank nothingness waiting to be defined. The moment you introduce an edge, you introduce a paradox. If something exists beyond it, then space hasn't truly ended. And if there's absolutely nothing, how can it be said to exist at all? A universe without edges avoids that confusion. It simply exists. You can keep moving forever, or maybe come full circle. There's no edge to fall off, no cosmic warning signs, and no need to define what's beyond the beyond. That doesn't mean we'll stop asking about boundaries. Our minds are wired to think in terms of containers. We like beginnings, middles, and endings, but the universe doesn't seem to care about our mental filing systems. It stretches, curves, and possibly loops, without offering a clean border to wrap it all up. Interestingly, even if space has no edges, time might. Our universe had a beginning, at least from our perspective, about 13.8 billion years ago with the Big Bang. That wasn't a point in space, but a point in time. A moment when space itself began expanding from an earlier state. Asking what came before the Big Bang is like asking what's north of the North Pole. It's not that the question is meaningless, it's that our usual coordinates stop working. Of this paints a picture of a universe that's far more subtle and strange than a giant box. It's not an object you can lift the lid on or peek around the side of. It's more like a melody playing forward, wrapping through dimensions and flowing through time with no final note, no ending chord, just endless variation. And in that melody, there are no hard edges, only connections, curves, and continuations. Whether it loops or stretches infinitely, the universe doesn't close off like a room. It opens up like an idea, not bounded by walls, but shaped by relationships, gravity, light, motion, time. So if you've ever imagined a spaceship sailing toward the edge of the universe, picture this instead. A long, quiet journey that never finds a cliff. Just more stars, more questions, and more space. Not because the universe goes on forever necessarily, but because it never had an edge to begin with. Before there were stars, before galaxies, even before atoms settled into their roles, there was light, a soft, uniform glow spread across the universe like a warm fog, stretching in every direction. It wasn't a spotlight or a burst of fireworks. It was quieter than that, gentler. Like the first rays of morning light slipping through a window before anyone wakes up, and some of that light is still here today. We call it the cosmic microwave background, or CMB for short. It's not just the oldest light we can see. It's the oldest light anyone can see. A whisper from the early universe, still drifting through space, passing through galaxies, stars, planets, and sometimes with the right instruments into our detectors. To understand where this light comes from, we need to go back in time. Bedtime. Back. About 13.8 billion years ago, the universe began in a hot, dense state, a singularity of seething energy and unimaginable temperature. In its earliest moments, space expanded rapidly, spreading out energy like batter in a pan. As the universe grew, it cooled, not instantly but gradually, like a cosmic kettle slowly removed from the heat. At first, the universe was a blinding soup of particles and radiation. Photons, the particles of light, bounced around constantly, trapped in a fog of charged particles. Electrons and protons zipped around separately, and light couldn't travel far before being scattered in a new direction. Imagine trying to shine a flashlight through a thick cloud. That's what the universe was like for its first few 100,000 years, opaque, chaotic, and full of restless motion. Then something remarkable happened. About 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This moment is poetically called recombination, and it changed everything. With fewer charged particles to bounce off, light was suddenly free to move, the fog lifted, the universe became transparent, and the first light broke loose. That ancient light, released across the cosmos, has been traveling ever since. It fills the universe in every direction, stretched out by billions of years of cosmic expansion. Once a searing blast of ultraviolet energy, it's now cooled to a gentle microwave hum, a whisper instead of a roar. But it's still here, all around us, passing through your room right now like a soft, invisible breeze from the beginning of time. We first discovered the CMB almost by accident. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were using a large horn-shaped antenna to study radio signals. They kept picking up a persistent background noise, no matter where they pointed the antenna. They cleaned the equipment, double-checked their calculations, and even removed some pigeons nesting in the device just in case. But the noise remained, steady, uniform, and strangely cosmic. What they had stumbled upon without realizing it at first was the afterglow of the Big Bang. It was the cosmic microwave background, predicted by theory and now detected in all its quiet detail. That faint hiss in their radio signal turned out to be a glimpse into the baby universe. Since then, scientists have mapped the CMB with incredible precision. Space missions like COBE, WMAP, and most recently the Planck satellite have given us a high-resolution view of this ancient light, and what they found is more than just a glow. It's a cosmic blueprint, a snapshot of the universe when it was less than 500,000 years old. At first glance, the CMB looks remarkably uniform. Same temperature, same brightness, no matter where you look. But zoom in and you'll notice tiny fluctuations, small warm and cool spots, just a few millionths of a degree apart. These gentle ripples aren't flaws. They're the seeds of everything. Tiny differences in density that over billions of years grew into stars, galaxies, and eventually you, sitting here listening to a video about the universe in your favorite pajamas. Those slight variations are clues. They show us how matter was spread out in the early universe. They reveal the physics of the cosmos at its birth, and they help us test theories about how space and time unfolded in the first moments of creation. Even the shape of the universe leaves its mark on the CMB. If space were curved like a sphere, shaped like a saddle, or flat like a pancake, those geometries would subtly affect how light travels. By measuring the size and spread of the fluctuations in the CMB, scientists can figure out the large-scale structure of space itself. And so far, all evidence points to a universe that's flat, at least within the limits of what we can observe. It's a bit like studying the ripples on a pond to learn about the shape of the shore. The way those waves stretch and move tells you something about the environment they're in. In the same way, the CMB carries encoded messages about the shape, size, and contents of the universe. It's light as data, photons as historians, and there's something deeply calming about imagining that glow, a soft, gentle wash of ancient light. Not blinding, not fiery, just calm and even. Not something you can see with your eyes, but something that's always there. It's like the universe's own lullaby, still playing after all these years. If you had the right kind of radio, you could tune into it anywhere. Not as music, but as a faint static warmth, a quiet, low-level presence woven into the fabric of space. It's the closest thing we have to a baby photo of the universe, a snapshot of its earliest moment of clarity. And it's still whispering to us, long after the stars were born, long after galaxies took shape, long after Earth began its slow orbit around the sun. That light has outlived generations of stars, crossed unimaginable distances, and arrived here in your lifetime, ready to tell its story. In a universe full of mystery, the CMB is something solid, something we can measure, map, and understand. It reminds us that we don't need to chase the edges of space to learn about its beginning. Sometimes the answers are already floating around us, waiting patiently in the glow. So next time you look up at the night sky, try to picture it not as black and empty, but filled with ancient light too faint to see. It's been traveling for over 13 billion years, stretching with every moment, carrying the quiet history of everything. And even now, in the stillness of space, it continues to shine. Is there a true edge to the universe? A final frontier? A cosmic curtain? Some ultimate boundary where space just stops? It's a question that keeps coming up, not just in science fiction, but in real scientific discussions, whispered between chalkboards and telescopes. While mainstream cosmology leans toward a universe with no hard edge, some speculative theories and thought experiments open the door to stranger possibilities, places where boundaries might exist, even if we can't see or feel them. Let's ease into one such idea, that our three-dimensional universe could be a kind of surface or brain, floating in a higher dimensional space. This is one of the central ideas in brain cosmology, an offshoot of string theory. In this view, our universe might be a vast three-dimensional membrane, short for brain, existing within a higher dimensional bulk. We're confined to this brain. All the particles and forces we know except gravity are stuck here like bugs on a soap bubble. Gravity, being a bit more adventurous, might leak into the surrounding dimensions. That's one reason some physicists think it seems weaker than the other forces. If this idea is correct, then our universe could have an edge, not in three-dimensional space, but in the higher dimensional bulk we can't directly perceive. You could imagine the brain having a limit or boundary in dimensions we don't experience. From our perspective, everything feels continuous and edge-free. But from the viewpoint of a hypothetical five-dimensional being with excellent eyesight, we might look like a cosmic disk, with boundaries around the rim. It's a little unsettling to imagine being observed by something with more dimensions than we can comprehend, but it's also oddly comforting. We'd be the strange mystery to them. Then there's the concept of cosmic domain walls, boundaries between different regions of space, where the laws of physics might vary slightly. These walls are predicted by some theories involving symmetry, breaking in the early universe. Imagine space undergoing a phase change, like water turning into ice but not freezing the same way everywhere. Some areas settled with one set of rules, while others took a different path. The borders between these zones could form domain walls, massive structures stretching across space, dividing one cosmic region from another. In most models, these walls would have quickly vanished or faded into insignificance, but in some speculative scenarios, they might still exist, hidden in deep space like silent guardians. Passing through one might be uneventful, or it might feel like stepping into a slightly different universe. Your atoms could behave a little differently. Your tea might taste just a bit more lemony, for reasons you couldn't explain. Speaking of crossing into other realms, some theorists have proposed that our entire universe might be inside a bubble, not metaphorically, literally. A bubble of space formed during a phase of cosmic inflation. Picture the early universe bubbling with quantum fluctuations. In some spots, inflation stops, and a bubble of space forms with its own properties, its own constants, its own gravity, its own number of dimensions. Each bubble becomes a universe. This idea is called eternal inflation, and it naturally leads to the concept of a multiverse, a frothy sea of bubbles, each with its own unique physics. In this view, there's a kind of edge where our bubble meets the inflationary background, or where it might someday collide with another bubble. But such collisions would be incredibly rare. If we're a bubble in a vast cosmic foam, our neighbors are too distant to ever meet. The edge of our bubble would be more theoretical than physical. Still, there's something poetic about imagining the universe as part of a fizzing sea of realities, each expanding into the void like soap on a dish. And then there's Gödel's rotating universe. Yes, that Gödel, the same mathematician who shook the foundations of logic with his incompleteness theorems. In 1949, he proposed a solution to Einstein's equations describing a universe that rotates as a whole. Not just galaxies spinning, but the entire fabric of space-time slowly twisting like a cosmic spiral. In this unusual model, time and space are curved in such a way that you could, in theory, follow a specific path and arrive back at an earlier moment, a time loop. Gödel's universe has no edges, but it blurs the line between spatial boundaries and causal ones. What's more disorienting? A wall at the end of the universe, or the ability to meet yourself before you were born? Now, before you pack your bags for a round trip to yesterday, it's worth noting that Gödel's rotating universe doesn't match what we observe. Our universe isn't spinning in that global way, and the time loops he described remain purely theoretical. But the model is valuable, not because it's realistic, but because it stretches our thinking. It reminds us that the universe follows equations, not our imagination, and sometimes those equations allow for worlds stranger than fiction. Another bold idea suggests the universe might be like a hologram, not in the sci-fi sense of flickering projections, but in a precise mathematical way. According to the holographic principle, everything that happens in our three-dimensional space might be encoded on a distant two-dimensional boundary, similar to how a hologram stores a full image on a flat surface. In this case, the true edge of our universe isn't a wall or a border, but a boundary where fundamental information is stored. We're not talking about simulations or digital illusions, just a different way of describing the same physics. The idea comes from string theory and black hole thermodynamics. It's still speculative, but intriguing. The deeper message behind all these theories isn't that we'll find a physical wall at the edge of space or a sign that says, "End of universe, authorized personnel only." It's that space might have boundaries in ways that don't resemble anything we're used to. Edges might exist in higher dimensions, in the universe's initial conditions, or in the information that underlies reality. They might not look like walls. They might appear as shifts in physics, changes in curvature, or alterations in the rules themselves. It's entirely possible that we live in a universe with no edge at all, but it's also possible that we're brushing up against ideas that feel like edges, limits to what we can know, what we can observe, and what our equations can describe. And that's a kind of boundary too, isn't it? We're creatures shaped to live in rooms on continents, surrounded by air and gravity and things that end. So when we explore cosmology, we bring those instincts with us. We search for edges because everything else in life has them. But the universe, as always, doesn't owe us clarity. Maybe the cosmos loops quietly back on itself. Maybe it stretches endlessly in all directions. Maybe it rests delicately on the surface of a higher dimensional bubble. Or maybe, just maybe, it's shaped like something we've never imagined. Something that curves, connects, and folds in ways our minds can barely begin to grasp. And yet here we are, floating in that mystery, wondering about boundaries while being part of something that might not have any. There's something peaceful in that, don't you think? That the universe could be endless, not just in size but in possibility, that even the questions themselves might stretch on forever. It's already a big challenge just trying to understand this universe, with its billions of galaxies, swirling black holes, cosmic background radiation, and space that might curve or stretch forever. We have plenty to think about, but every so often cosmologists and physicists stir the pot and ask an even bigger question. What if this universe isn't the only one? Welcome to the multiverse hypothesis. It's one of the most fascinating, bizarre, and thoroughly speculative ideas in modern physics. It suggests quite simply that there might be more than one universe, maybe many more, maybe even infinitely many. Universes with different physical laws, different particles, different timelines. Universes where cats walk on ceilings, gravity flows sideways, or your high school haircut turned out way better. Before we go too far, let's be clear. There's no direct evidence for other universes. None. We haven't seen them, measured them, or waved to them across a dimensional fence. The multiverse is a framework, not a conclusion. A way of thinking that arises naturally from certain theories, but still lives in the realm of speculation. That said, the idea isn't as wild as it sounds. In fact, there are several versions of the multiverse hypothesis, each with its own flavor of cosmic imagination. The first and most intuitive is called the cosmic multiverse, or bubble universe model. This idea comes from inflation theory, the rapid expansion that followed the Big Bang. According to this view, inflation didn't happen evenly. Instead, it could have created many separate bubbles, each forming its own universe, expanding and evolving on its own. Each bubble might follow its own laws of physics. Some could be too strange to support matter. Other bubbles might contain entirely different particles, forces, or even dimensions. We happen to live in one of the fortunate ones where conditions are just right for stars, planets, and long-winded late-night podcasts. In this bubble model, our universe is like a single soap bubble floating in a cosmic foam. Other bubbles might be out there, drifting endlessly, forever separate from ours. If you're picturing a cosmic sink full of dish suds, you're not far off. Then there's the quantum multiverse, which comes from interpretations of quantum mechanics, specifically the many worlds interpretation. This version suggests that every time a quantum event has multiple possible outcomes, all of them actually occur in separate branching universes. So in one universe, you hit snooze this morning and stayed in bed. In another, you got up early and made pancakes. In yet another, you tried to make pancakes but accidentally discovered teleportation. Each branch is a new version of reality, created by the unfolding of every possible choice and chance. This isn't just a thought experiment. It's a serious interpretation of quantum mechanics, developed to avoid the awkwardness of wave function collapse. But like the bubble universe idea, it's not something we can currently test or observe. We can't hop between these branches. There's no interdimensional train station, with a mustachioed conductor offering trips to the universe where you became a world-famous harmonica player. And yes, in at least one of those infinite branches, you probably have a mustache. Even if you've never grown one. Statistically speaking, it's almost guaranteed. Somewhere out there, you might be giving a TED talk about alternate facial hair choices and their impact on parallel timelines. There's also the mathematical multiverse proposed by cosmologist Max Tegmark. This idea suggests that all mathematically consistent structures exist as physical realities. In other words, if it's mathematically possible, it exists somewhere. That includes not just other universes with different particles, but ones with entirely different logical rules. Universes where the value of pi is different, or time flows in spirals. It's a bold idea, almost mystical in scope, and probably impossible to test, but it's compelling to imagine that math itself could be the foundation of existence, spawning every possible variation of reality like an infinite library of cosmic blueprints. These multiverse ideas, while fascinating, do face criticism, and rightly so. One of the biggest challenges is falsifiability. If other universes are forever inaccessible, how do we study them? How do we know they exist at all? Science works best when we can test predictions, measure outcomes, and refine our models. When we're talking about realms that can't be reached by any signal, it's hard to apply the usual scientific tools. Some physicists see the multiverse as a warning, a sign that theories are stretching beyond their useful limits. Others argue that the multiverse helps explain why our universe has the properties it does. If there are countless universes, each with different constants and laws, it's not surprising that we live in one where life is possible. It's a cosmic version of survivorship bias. We exist here because here is a place where existence is possible. It's like rolling dice in a casino with an infinite number of tables. Most tables produce nothing interesting. But at one of them, by pure chance, the dice land just right. That's the table we're sitting at. We didn't cheat, we didn't rig the game. We just happened to be in the room where the numbers worked out. Some cosmological models even suggest that multiverses might be indirectly detectable, perhaps through unusual patterns in the cosmic microwave background caused by collisions between bubble universes. So far, nothing has shown up, but physicists are keeping an open mind. After all, some of the most remarkable discoveries in science began as strange ideas waiting for the right tools. Whether or not other universes exist, thinking about them stretches our imagination. It encourages us to look beyond the limits of what we can see. It reminds us that reality might be broader, stranger, and more playful than we ever expected. It invites us to be humble about what we don't know, and bold in exploring what we might someday learn. And really, isn't that what science is all about? Not just answering questions, but discovering bigger ones. Not just building knowledge, but expanding wonder. Even if we never find another universe, even if this one is all there is, we've already shown that human curiosity can reach across galaxies, through time, and into ideas as vast as the multiverse itself. That's no small thing. So whether you believe in a single cosmos or an infinite stack of them, whether you prefer one timeline or a branching forest of quantum possibilities, remember, somewhere in the multiverse, you're doing something brilliant, or unusual or inexplicably involving a llama. And in this universe, you're here thinking about space, sipping tea, and quietly wondering what else might be out there, just beyond the veil of what we know. That in itself is a kind of cosmic magic. Where does space stop? It's the question that brought us here, whispered softly at the beginning, like a child asking if the sky has an end. And after wandering through galaxies, curved dimensions, cosmic microwave whispers, and edges that may or may not exist, we find ourselves gently circling back to where we began, still wondering. We've learned that space doesn't behave like a room or a box or a stretch of road. It doesn't come with a fence or a finish line. It doesn't need walls to be complete. It can be infinite or finite and unbounded. It can stretch, loop, curve, and fold in ways our minds are only beginning to grasp. It can even carry galaxies, away from us faster than light, not because they're moving, but because the space between us is growing. We know there's a limit to what we can observe, a cosmic horizon beyond which light hasn't reached us. But we don't know what lies beyond it. Maybe the universe continues forever, or maybe it folds back on itself in a gentle arc we'll never see. Perhaps our universe is one bubble among many, drifting in a higher dimensional sea. Or maybe the multiverse is just a poetic idea, beautiful but unreachable. What we do know is that space isn't empty. It's full of structure and subtle energy. It stretches with time. It carries the light of ancient stars and the hum of the Big Bang. It has no center, and as far as we can tell, no end. And still, questions remain. Is the universe infinite, or just very large? Is it curved, flat, or something else entirely? Is it one of many, or all there is? And if there were an edge to space, what would be on the other side? We may never find all the answers, but that's not a failure. It's the heartbeat of science. The beauty of the cosmos isn't just in what we know, it's in what we don't. It's in the quiet courage of looking up and asking. And so the search continues, as it always has, through telescopes and equations, through gentle dreams and midnight thoughts. Every photon we catch, every map we draw, every model we refine brings us a little closer. Even if the destination keeps shifting like the stars, maybe that's the point. Maybe space never stops, not because it's infinite in size, but because it's infinite in mystery. Maybe it doesn't need to end to matter. Maybe it just is, sprawling quietly in all directions. An invitation, not a boundary. At the beginning, I asked you a few things: where you were listening from, what time it was, and whether the question, "Where does space stop?" might keep you awake or lull you to sleep. I hope by now you feel more relaxed. I hope your thoughts have softened into that quiet space where wonder lives. And if you're still awake, just barely, I hope you found some peace in the asking, even if the answer remains elusive. Because really, that's what space gives us. Not just stars or silence, but the freedom to ask the biggest questions of all. And maybe space never stops, because questions never do.